Well, actually, I guess I've known him since the 1990s. He was at undergrad at MIT, did a PhD in Berkeley. He's been a professor at Princeton in the meantime. So he's won all kinds of awards. He has 2 Google awards, the one in 2001 and one in 2010 for work on probabilistic checking. Euclidean traveling salesman problem. In 2012, he won the Fulkerson Prize for Sparse pet work. He won all kinds, and he also has, I guess now it's called the ACM Prize in Computing. Used to have some funny name, the ACM Input System Award. But anyway, so. Sorry. Okay. And anyway, so of course he's worked in all kinds of areas, from complexity theory to geometric problems to, and in his most recent work, as it's quite common for many people after they've conquered all these other fields, to go and work in machine learning, and then he was no exception to that rule. And today he's going to talk on Bohr's theoretical understanding of semantic coding and hashing. Sanjeev, it's all yours.
Thanks, Gary. Yeah, it's always fun to be back here. And lovely new building, at least since I was last year. This is joint work with a fantastic team, Yuanji Li, Tengyu Ma, Yingyu Liang, Tengyu Ma, and Andrei Richteski. And maybe we should, lower the shades.
The lights need to be turned off.
The light?
Both.
We're supposed to do this. I think one of those.
Oh, there's shade controls here. Should I do those?
That's the wrong way. Otherwise.
Both screens.
Okay. All right. So 2 screens. Is that?
Yeah. So there. I thought we pushed full screen, but.
So I think.
Okay. Oh, good. It's both screens. Okay. So and the last 3 are on the job market in the spring, in case you're looking to hire. I recommend all of them. All right, so the topic of today's talk is semantic coding and hashing. So semantics as in like extracting meaning. So you're given some object and you want to extract its meaning. And let me start with a simple example. So what I mean by that. So which pair of sentences is most similar in this? Okay, so read this. The tiger rules this jungle. Milk flowed out from the bottle. Carnegie is a generous man. A lion hunts in a forest. And Pittsburgh has great restaurants. Does it not? Does it not is what I mean. Which pair? 1 and 4, correct. Right? So 1 and 4. But notice that they have no words in common. Right? They have no words in common. And so actually, towards the end of the talk, I'll show you a way to compute some similarity scores between these things. And so the similarity score, which I've normalized to 0 and 1, between 1 and 4, between 1 and 4 is 1. The ones you found were most similar. Between 3 and 5 is 0.57. Anybody has a guess why these and this are somewhat similar? Yeah, Carnegie is associated with Pittsburgh. And then between 2 and 5, it's 0.3. Okay? But 0.3 is low enough that probably is not so meaningful. Okay, so all right, so history. So I have various historical vignettes, and the first one is this paper by Hinton and Russ. Russ is here or no? Oh yeah, there you go. Which was when I saw Russ's talk on this many years ago, it had a huge effect on it. I don't know if I ever told you that. And here was the point of the talk, as I understood. Okay, maybe this was not Russ's message, but that's the message that got across to me as a theorist. So main point 1 was approaches like nearest neighbor assume that meaning or semantics resides in some metric class, right? So I was discussing with Gary. So like similarity equals small L sub p distance. Okay, and the point is that this is false in most settings, including text. Okay, as we saw in the previous example, right? Those two sentences we knew were similar, but they had no words in common, right? So no kind of L sub p or distance metric would pick up, right? All right, and or you know, like two paragraphs that are about politics, right? They may not have any common word, but they may both be about politics. Okay, so main point 2 was that meaning is a latent structure, which can often be recovered in their case, in that paper, using Hinton's restricted Boltzmann machine. And they showed experiments which showed that it beats the theory ideas like nearest neighbor search or locality sensitive hash and so on. Okay, precisely because of this reason, because these hashing methods assume that the distance corresponds to similarity, but it's not true, right? Yeah.
Do you mean by, do you just mean that you can't compute this as a metric from some simple considerations like
That's right.
the words, or do you mean that the triangle inequality doesn't work for similarity of sentences?
Yeah, no, that, you know, yeah, if you're thinking of it as, you know, what words are in there, okay, they look like completely unrelated. Okay? So possibly for half of the audience here, this is completely obvious, but for the theory part of the audience, I can assure you, this is a revelation, okay? When I saw Russ's talk 5-6 years ago, it was a revelation. Like, to think about it this way. Okay, so what is the restricted Boltzmann machine? Again, probably half the audience knows it very well. So it's some kind of a model where there are visible units and hidden units. So visible units think of it as text, and hidden units is the latent structure. And it assumes some kind of a model. It's kind of like an Ising model, which it's an energy-based model which describes the joint distribution of x and h. And there's a quadratic energy function. And so given x, which is this text you're seeing, so firstly you train this model using a large corpus. Okay? So you train it with large corpus, lots of text. You train this model, you learn these weights of this Ising model. And now, given a new piece of text, you map it to the most likely value of h. Okay? So that's your semantic representation. Okay? The latent representation. And that's their semantic hashing. Okay? Or semantic coding. Okay? All right. So, all right. So by the way, we were thinking about this and with my student Risteski, and you know, for the theorists here, you know, you can illustrate this phenomenon using very simple mixture models. You don't need a complicated model like RBM. You can illustrate with a simple mixture model. I have a manuscript if anybody's interested. It's not published. Okay. History B. Word embeddings. So these are very popular in information retrieval and natural language processing. You can imagine that these kinds of abilities that I talked about are very important, say, in web search, right? Web queries may be related even though the words are not the same. So word embeddings capture each word with a vector. And this vector is computed by studying a corpus, a large text corpus. And it turns out that human judgments of word similarity correlate with vector inequality. Okay, so these learned vectors somehow represent human notions of similarity. Okay, so cosine similarity, just the cosine of the angle between them. And what really, so this area has existed since 1990, and it was popular in information retrieval, but there was this paper from the Google team on Mikulov et al., which really made this extremely popular in the last 3 years. And it showed that there was a way to compute word embeddings such that you could solve word analogy tasks via linear algebra. So I mean the following. So you have a linear analogy task like man is to woman, king is to. So these are standard tasks in NLP to test understanding of language. Also, you know, for humans, you know, psychologists test kids with analogy tasks, and if they can't solve analogy tasks, they think there's something wrong. Okay, it's a test that child psychologists use. So, all right, so they showed that with the word embeddings they had, which they showed how to compute, which I'll talk about in a second. So if you're trying to solve this man is to woman, king is to, you take the vector for man and woman, take the difference, and now you look for, this should have appeared here. So you look at the vector for king, you look at the embedding for king, and you look for a word over here such that this difference is as similar to that difference. And this word happens to be queen. Okay? And they were able to solve something like 70–80% of the tasks in some standard test bed using this linear algebraic method. And notice that 60–70% is very good because there are 100,000 words in the dictionary. So there are 100,000 possible examples. So random guessing would not get you anything, as opposed to binary classification where random guessing gets you 50%. Okay, so this is very impressive. And formally, this is the objective function. You're looking for the vector, the word W here, so that you minimize the squared difference between these two displacement vectors. Okay. Anybody in this room who'd never seen this before? The analogy solving with linear algebra? Just here. So quite a few. Okay. All right. So those were my two historical slides, just to show that people have been wrestling with this for a while, and there's some interesting things out there. And so, which brings us to the question: what is meaning, and how can mathematics capture it? And the goal is clean models and provably correct outcomes. So, yes, I come from the theory world, and yeah, things, when things work, there's some model, a neural net or whatever. I want to understand why does it work? What is it really picking up on? Right? What structure is it really picking up on? So that's what I mean by models. And we will restrict attention to text in this talk, although recent work by others suggests similar ideas apply to collaborative filtering, vision, etc. Any questions so far? Okay. All right. So how do you capture meaning, right? So I posed this question: what is meaning, and how can mathematics capture it? Right? It seems so nebulous because language is so nebulous. All right. So here's a quick thing. Think of a word that co-occurs with cow, drink, babies, and calcium.
Sorry.
Cow, drink, babies, and calcium. Milk. Okay? This is a simple example that illustrates that the word milk is in some ways captured by the fact that I told you that it occurs with those four words. Right? It's some kind of a social network notion of meaning, right? That those words had some meaning. How we got those, we don't know. But given that those meanings have been understood, milk is understood, right? It's some kind of social network of meaning, right? So formally, this is the distributional hypothesis of meaning by Harris and Firth, linguists in the 50s, who said, who thought about this for a while, and they said the meaning of a word is determined by words that it co-occurs with. Okay?
The meaning of the word is
determined by words that it co-occurs with in text. Okay? Co-occurs with often. This is not a perfect definition. Linguists have debated it, and there's disputes, and there are counterexamples, etc. Okay? But it is a very good starting point. Okay, so if that is our meaning, here is a very simple high-dimensional word embedding for the word W. Namely, just give me the empirical distribution of all other words around it in text. Okay, take a large corpus and let this entry m sub wc. So I'm writing a vector for the word W. So m sub w is its embedding, and its seed coordinate for word C is the probability, the empirical probability that words W and C co-occur in windows of size 5 in the corpus. Okay, so I take this large corpus like Wikipedia, look at windows of size 5 adjacent words, and how often do W and C co-occur? Okay, so how often does milk occur with cow, with drink, etc. Okay, so it's a very high dimensional vector. In fact, the dimension of this vector is 100,000 or something like that, the number of words in the dictionary. Now, it turns out that's of course a representation of meaning, but Church and Hanks, two linguists, actually suggested even about 30 years ago that there's a better measure, or better vector, which uses point-wise mutual information. So this is a different vector, n sub w, where the seed coordinate is not this joint probability, but essentially the log of that joint probability divided by the product, okay? The product of the marginals. So the joint probability divided by the product of the individual probability. So PW and PC are the probabilities of the word in the corpus, how many times it occurs, and PWC is a joint probability, okay, in windows of size 5. This, if you look at it, is a correlation measure, right? So PW and PC are the probability they occur independently. The product is some kind of like if they were occurring just randomly by chance in a word salad, and PWC is the actual game probability. Okay, so that ratio is a measure of correlation, and you take the log of that. And this log is actually important. So this is called PMI. So that turns out it's better embedding and works better in many tasks. And even better is a dimension reduced version of the above ideas. You can do it by singular value decomposition of the matrix, and you can do it by neural nets. Okay, make a little bit out. Okay, so which I'll talk about next. Okay, so you dimension reduce. So this 100,000 dimensional vector, you reduce to like 300 dimensions. Questions? Yeah. 5 is arbitrary. Yeah, could be 7, 10. And there's some differences in the embeddings you get out of that. 3, yeah, you could try that. Okay, so yeah, this is the important thing, that this kind of measure, and the thing I want you to focus is that it's non-linear. Okay, so you have to compute this statistic and take a log. All right, so history C, neural language models. In about the last decade or so, these have become very popular, and they've caused a revolution in NLP. Again, not news to probably a significant part of the audience. The idea in all neural language models that I know of is that you have some kind of a recurrent neural net, and this neural net is being trained to predict the next word. So if given the last few words or the context, if you can predict the next word with good probability, it means you've learned language. Okay, and so that's sort of the hypothesis. And so what does it mean to train to predict the word? It gets positive feedback if the actual next word had high probability, and negative feedback otherwise. Okay, you can formalize that in various ways, max likelihood or something, but that's right. Okay. So in Mikolov et al., there was a simple functional form. They had actually various models. This is the simplest one called the CBAO, which was that you use a simple functional form where, so here's what's going on. So this neural net has some internal representation of each word. Okay, these representations will turn out to be word embeddings. So there's a vector of parameters for each word, and given the last 5 words will be the W1 through W5, you take their word vectors, take the average, and then the probability of the next word being W is proportional to the exponential of the inner product of VW and this average vector. Okay, so this is some kind of a context vector, the average of the last 5 words, and this is the next word. Okay, roughly that's the model. Okay, so this neural net is initialized with no idea of word embedding, just random vectors, and then it trains itself as it reads the text to fit the word embeddings better and better to this form. Okay, and then those word embeddings that you take at the end have those nice properties. Turns out this is an empirical fact. Okay, that you can solve analogies and so on. Questions? Yeah.
So this is the predictions you use in the 5% numbers?
The 5.
Was the 5?
The windows of 5. Again, 5 is not important. It could be 7.
No, is a window that surrounds the word? Because then you can't predict them.
Yeah. So that's actually an important thing. Yeah. There's a detail that actually the better model is that you look at the 5 words surrounding, not just the previous 5. Yeah. Any other questions? Okay. So Quiros et al., I think Russ was a co-author on it. Yeah. Use similar ideas to create sentence and paragraph embeddings, for instance, skip thought. These are useful for NLP tasks like spotting paraphrases, sentiment analysis, and so on. Okay. We'll return to sentence embeddings and paragraph embeddings later. Okay. So the rest of the talk, I'll try to develop theoretical models that explain what latent structure is being captured by such semantic coding and hashing. Okay, and this is going to feature a surprising confluence of new and old methods that were earlier considered distinct, like RNNs, RVMs, PMI-based embeddings, skip thought, etc. Okay, and the idea here. So, what do I mean by a theoretical model? So, imagine the writers of Wikipedia or some corpus. So there's a bunch of people, okay, and they are outputting words, right? Sequence of words. As they were outputting that word, there's some semantics in their head, right? And that's what we're trying to understand, right? The semantics of text. So that semantic was somewhere in their head, so that's kind of like a latent variable, just like in the Hinton-Salafold paper. So there's some latent variable which corresponds to semantics, which leads to the production of words, okay? And now if you have a suitable model, you know, this model, what it predicts, you know, what the word, what corpora look like, will fit some of these empirical facts, right? That word embeddings exist, low-dimensional word embeddings exist, they can lead to solving analogies, etc. Right? So you want some model of this process so that the output has the nice properties that are being exhibited empirically. Okay? So the first question is, why do low-dimensional word vectors exist? So let me clarify what do I mean by that. So remember even the old PMI method, the Church and Hanks method. So for every pair of words W and W prime, you compute the PMI, which was this nonlinear measure, the correlation measure. And then a simple embedding would be to take a 300-dimensional squishing of this large matrix. This matrix is 100,000 dimensional, right? 100,000 rows and columns, one for each word. And you take a low rank approximation of this matrix, and that's your 300-dimensional word measure. Okay, and it's known, Levy and Goldberg argue this in some heuristic way, that GloVe and Word2Vec are fancier versions of this idea. So the question is, what property of language causes this 100,000 by 100,000 matrix to have approximate rank 300? Right. So that's the. So as a theorist, you know, you look at it, and there's some matrix being defined using some empirical stuff with a nonlinear transform of the empirical observations, and then that matrix turns out to have low rank. I mean, that's very striking. So what is this model of this Wikipedia writer which leads to that behavior? Right? All right. And the main issue here is nonlinearity or logarithm. If you replace PMI with some straight measure like joint co-occurrence, then there is an explanation which is topic model, which is something I've also worked on, but is not the subject for today's talk. Any questions? Okay, so what is this model of Wikipedia writers? Okay, so of course it's going to be a simplified model, stylized. And this was a paper in Tackle. So it's actually a dynamic version of a loglinear topic model, which is due to me and Hinton. So we came up with this loglinear model, and then we showed it to people, and then at some point we heard that this is very related to me and Hinton, and we went back and saw, yeah, it is. So the only change is that it's a dynamic version. So let me tell you what the dynamics is. So we assume that inside the writer's head, there's a semantic space. And each, so which is a low dimensional, 300 dimensional, okay? R to the D dimensional, R to the D is the space. And let's say the sphere in R to the D. And each dimension or each direction in this space, not dimension, each direction in space is associated with a discourse, which is, think of it as a narrow topic. And so that's the point over there, okay? And that's a discourse. So what does that mean? So a discourse is about what you talk about, right? And so each word is also associated with a vector VW in RD. These are latent variables associated with the semantics. So each word has a vector in this space also. And so when the writers are generating Wikipedia, this discourse vector is doing a random walk in discourse. That's what we do. So the corpus is generated by a random walk of a discourse vector on the unit sphere. And the probability that the word is output when this random walk is at some point ct, at time t, is proportional to the exponential of the inner product of VW and ct. So notice what this is saying. So when the walk is over here, at this point, all the words that are near that point have a higher probability of being output, right? Because it's proportional to the exponential of the inner product of the word and ct. And all the points that are sort of far away from it will have lower probability. Okay, so it's sort of like a searchlight that's moving in the space, and as it comes to a point, it tends to output words that are close to it. Okay, and by the way, this is very reminiscent of RBM. Okay, remember the RBM also had some exponential function, except the coordinates of the C's are IID. Okay, it's doing because C, this vector, the discourse vector is doing a random walk. Okay, so it's a dynamic model. Question?
The random walk is independent of this topic. You have this fixed topic vector.
It's not a fixed, no. There's infinitely many topic vectors. Okay, every direction in this space is a topic, a very narrow topic. And the random walk is sort of moving around the space, and when it's at a certain point, it tends to emit words that are close to that.
Oh, okay.
Just tends to. Of course, there's some probability of emitting any word whatsoever. Uniform over the sphere. Yeah.
Do you only care about the angle, or do you also care about the magnitude?
The magnitude, this is only the, oh no, sorry, this is the inner product, not the angle. This is the inner product. So I was, yeah, magnitude is important as well. Absolutely, yeah. Yeah, there is vectors here, word vectors which are long, and that's actually important. Because, empirically, some words have higher probability of occurring just because they're popular words, and you absolutely need the magnitude. Yeah.
Every word here once, or we have multiple copies?
You can output the same word, yeah. I mean, that would be nonsensical. Normally, you don't have two words next to each other, but there's a low probability.
He's talking about type tokenization, I think. So each type only occurs once, right? In your sphere.
Milk, how many times does milk appear here?
Once. On this sphere, yeah. But it could be output multiple times. So this is a process of outputting words. Yeah. But in this space, milk only appears once. There's one vector. Good. Excellent. The question was, what if the word has 2 minutes? Very nice question. We'll get there. That was actually a mystery for word embeddings. And we'll have an answer. Any other questions? Okay, so okay. So the question is, what distribution on bigrams, like pairs of words, does this process generate? Yeah, what was your question? Okay, so by the way, this is just an illustration. The only thing that is showing is, what is a random walk. So Yingyu took an actual paragraph, okay, from some history thing, and he fitted, we've already fitted our model, and he reconstructed what random walk gave rise to this paragraph, okay? This is not synthetic test. This is like, take actual text and fit an empirically a random walk. I'm not saying much, okay, just showing you what random walk is and how it's emitting words. Okay, all right, so how do we analyze this thing? So a key assumption is going to be spatial isotropy of word vectors. Okay, so in general, there are all these models in machine learning, and reasoning about them is very hard, like, RBM, or, these are Ising models, or doing anything with them is NP hard. So it's very hard to get any theory going. And to get any reasonable theory, you have to make assumptions, okay? So here, the assumption we came up with, it seemed like the only possible assumption that could explain all the things that were going on, was that these word vectors inside the writer's head are spatially isotropic. Like in this unit sphere of meaning, they are kind of spatially isotropic. So
what happened with the little trivial words like in and the in that example? Like, because those are output all along this walk. So
that's right. So
that'll be a trivial question.
yeah, let me get to that later. Okay. Yeah. Okay, so right, so like any simple model, right? So making it high fidelity, like if you actually try to output text with it, it will often look very nonsensical. This is capturing like latent semantics, yeah, which is not so much carried by A's and R and so on. Okay, that's maybe a rough answer. So in the bulk, they behave like a set of random vectors in D dimensions. So scaled normal vectors. And So the reason that's very nice is that in this probabilistic model, there's something called the partition function. So when your context is C, this is some kind of a normalizing term in the probability model, which is the sum of all these exponentials of VW times C, which is called a partition function. And if these word vectors are kind of isotropic in space, as this random walk moves along the space, this stays constant, or roughly constant. Okay, it's tightly concentrated. This is a hypothesis. Okay, this you may or may not like, whether they really behave like normal variables, and that's actually related to some musings in linguistics that people have done. But this is empirically testable, and this is actually okay. So you fit the vectors according to this theory, and then you see that actually yes, the partition function is very tightly concentrated for most C. And in fact, then we discovered, after we'd done this, we came up with this just from pure theory, and then at some point we learned that there's a trick in natural language processing called self-normalization, where you have these loglinear models and you ignore the partition function. Just assume it's constant. Okay, and that works okay. So that's an empirical trick. Okay, so that's related to this. So assuming that, we have a theorem that if the discourse vector at time t is like this, right, the model that I said, the discourse space is a unit sphere, and CT is doing a random walk, slow random walk, and VWs are spatially isotropic. Okay, these are the mathematical assumptions. Then the main theorem is that the PMI of the pairs of words W and W prime that you'll see is exactly the inner product of VW and VW prime, these latent vectors, plus minus a little bit of error. And the log of the probability is proportional to the square of it. Okay, this D is just a dimension, it's just a scaling. Don't worry about it. Okay, and there's a term here Z, which is a constant, which is a partition. Okay, so you get this kind of behavior, and actually this fits reasonably well. And so what this is saying is that the norm of the word vectors determines frequency, that's this one, and the spatial orientation, which determines its inner product with others, determines co-occurrences, which determines mean. Right? Because according to the distributional hypothesis, co-occurrences determine mean. So the spatial orientation determines mean. Okay, so this actually fits within 17%. There's actually a different expression which you get which fits even better, which I won't talk about. But I'm talking about this because PMI already introduced, so I'm just telling you. So this answers the first question I raised. Why do low-dimensional word embeddings exist? The answer is because the process inside the Wikipedia authors is something like this, and if it's like that, then you get this empirical. Okay, so can you derive existing embedding methods with this? So yes, so it turns out that the previous nonlinear embedding methods like word-to-vec and glove are approximations to max likelihood fit to our model. So yeah, it is mostly for experts. If you know what glove was, we get a very similar expression. And if the last 5 words were W1 to W5, then the map estimate of the discourse vector in this random walk is the average of the word vector. In fact, this is how Yingyu created that animation of the random walk that I showed you. Okay? So those are related. Now, so how do we train our word vectors? It's using this objective, which is, if you think about it, again, only for the experts, is some kind of low-rank matrix approximation. You have inner products here, which are approximating some empirical quantity, which is weighted SVD. This turns out is NP hard, okay, even for 2-dimensional approximation. But our training objective is just weighted SVD, which can be solved in practice by gradient descent by adaptation. This is one of those amazing things in machine learning today, that there are all kinds of NP hard problems that seem to be solved by some variant of gradient descent. And so this is a very interesting phenomenon which my group worked on as well. You know, why do these algorithms work? That's not the subject of this talk, but yeah, some of my co-authors also have polynomial time algorithms for weighted SVD when the weights are randomized. Okay, second thing, why do relations correspond to direction? Okay, that's another empirical fact about word embeddings, and how can we explain that? Now, this actually was a controversial thing before our paper, and for all I know, it's still controversial. But Levy and Goldberg, in a very well-known paper, claim that actually they don't. That this is a misinterpretation of the Mikolov et al. Experiment. And they gave lots of anecdotal counterexamples. And this is in general true for anything you'll say about language or linguistics. There are always counterexamples. Okay, so that's not the way to look at it. So here we give theoretical support for the following interpretation of the relations correspond to lines. That for every relation R, there exists a direction P sub R such that if A and B, two words, have this relation, like masculine, feminine, man, woman, then the difference vector is this direction, this relation direction, plus noise. Okay, and this noise is fairly small. And actually, Lisa Lee, who's a grad student here now, when she did her undergrad thesis, she actually gave empirical support for this. I mean, that's when I became a believer in this. I asked her to do this using free-based relations, and this was true. And that's when I said, okay, this is an interesting fact that needs a theory. Okay. So thank you, Lisa. Okay. So what is a relation? Okay. So what's the theory that explains this? So what is this masculine feminine relationship? So we say, okay, how do you formalize that two words have this relationship? And this is a suggestion from this Glove paper of the Chris Manning group. So which is that a relationship you should think of as, king, queen, and man, woman have a relationship because the probability for most words chi, the probability of a word chi occurring in the neighborhood of king, conditional on king, and conditional on queen, that ratio is the same for king and queen and man and woman. Why? Well, if chi is unrelated to gender, like eating, walking, then the two probabilities, the denominator and numerator, are roughly the same. So the ratio will be 1 on both sides. But if the word is not unrelated to gender, like dress or John, well, dress occurs much more with the feminine gender and John with the masculine. So for dress, both sides will be less than equal to 1, right? At least the deviation from 1 is in the same direction. Both sides will be less than equal to 1. Dress will occur more next to queen than to king, and more next to woman than to man. So both sides are less than equal to 1, and for John, both sides are greater than equal to 1. Okay, there are more men and more king named John. So you formalize this as a relation R is where for all the neighboring words, the ratio of these probabilities is some number mu sub R of chi, okay? So it's some function of the, for every word it gives a number, plus noise. Now this noise could be very, very high, okay? This property may be very, very noisy, okay? So clearly it's true because if the noise is very high, sure, it is true, right? If you allow the noise to be very high, sure it is. Everything. Okay, so Pennington et al. Had tried to show that this explains successivity solving, and there was something mathematically incomplete and incorrect there. So because they ignore approximation error. I mean, I won't go into the technical details. So what we show is a purification theorem. That if word frequencies have that property, and those words are generated using our model, right, this random walk model, then our model implies that for such a relation R, there is a direction P sub R such that for the word vectors, the difference is P sub R plus a much smaller noise. So that's why I call it purification. That when you look at the word embeddings, this is very small, okay? And that's what Lisa's empirical investigation shows, right? This noise is not so large, okay? So there is a direction associated with these relations. So proof uses the theory of linear regression if you're interested, and it uses this fact that the word vectors are isotropically distributed in space. Okay, so I won't say much more about the proof. Any questions? So this is in the Tackle paper still. Now this is the second paper, okay, which addresses your question. Polysemy. Words have multiple meanings. And this is something that's always perplexed NLP researchers. How does a word vector contain the various meanings of the word? Okay, so like tie may refer to the article of clothing, or tying somebody, or a match that's being tied, right? A tie. So how does vtie, this one embedding we compute for the word, contain these multiple meanings? Okay. So all right, so this is polysemy. So Pi represents so we thought about it the following way, and this was clearly inspired by this linear algebraic approach. We thought about it and we said this has got to be what's happening, and then we verified it. So the way to think about it is that Ti represents multiple words which happen to be represented by the letters Ti, right? Ti1, Ti2, Ti3, and they're represented. So of course they might be connected in some way, but they're very different words, and they're represented by the same letters Ti. So you can try the following thought experiment, right? So suppose the process of creating polysymous words is that you take unrelated words and combine them into a single word. So take two random unrelated words in the corpus, W1 and W2, where they have very different frequencies, and you declare these to be a single word. Okay? So take two words, erase them from the corpus, and replace them by the word XYZ. Okay, some new word. And now you create an embedding for this new word XYZ. So you retain the embeddings of all the other words, just W1 and W2 are erased and replaced by XYZ, the word. And now you can compute an embedding for this, declare this to be a single word, and now the question is, what would be the embedding of this new word? Okay? What would be the embedding? And the answer is, it's a linear combination. Okay? It's very close, like within 3% or something, of some linear combination of the two component words. Okay? And these coefficients, like 0.9 and 0.2 or whatever I came up, these are much more reasonable compared to the frequencies. One word was 100 times more frequent than the other, but the coefficients are not linear in that. Okay? And that's a great thing. Okay? That's what I think is going on with these word embeddings and why they are so useful. Because this way of these coefficients, suppose this coefficient was 100 times smaller than that coefficient, then this would be a very poor representation of meaning, because it would be swamped by norms, the less frequent meaning. But because the less frequent meaning has actually a fairly large coefficient, it's not swamped by norms. That's what's going on. So this is an empirical fact. This is not theory. Okay? We explain it by theory, but this is an empirical fact. You take random words, pairs of words, create new words. This is the behavior you see. You can look at the graph and update it.
And if we just accept this, then how should the random walk behave differently with respect to the union of these two words versus them separate?
It has to do nothing. The random walk is the same.
So it will use the combined word as
right.
as often as it would the same.
That's right. Yeah, so that's our explanation.
Yeah.
That in that model, you see that the new word vector will be actually roughly of this kind. Yeah.
So the problem that feels like this would cause is that, many words are polysymous.
Yeah.
And you're averaging together all these different semantic directions, you think you end up with something that's not interesting.
The fact that word embeddings are interesting is undeniable, right? So, and this, I'm telling you, is also a fact, This is not a theory, this is not a conjecture, this is an empirical thing, right? So your question is, why are they useful, right? So you can see, for instance, like the masculine...
Cause lots of trouble.
Right, but you can see, actually, it's funny you say that, because to me, when I see the previous theorem, right, that relationships correspond to lines, now a word is part of many relationships, right? And all of those have to be lines. So the only possible way meaning could reside is in a linear superposition. Otherwise, you wouldn't have lines corresponding to all the relationships that this word. So to me, it was like the opposite reaction to what you said. The fact that all these relationships are lines, as Lisa showed, empirically, suggested to me strongly that this must be true, and that's why we did this experiment. Yeah?
So how about we teach this experiment?
Good. Let's see.
You make the frequency of the different...
Up to a few hundred. Up to a few hundred.
Did you make them equal?
Yeah, we have the plots, from equal to...
And multiple copies, like 5 or 10 different meanings?
Yeah. Oh, we haven't done the experiment with 5, no. So clearly, you would still continue to get linear superposition, right? If you are combining 4, it's like you combine 2 first and then the 2, right?
Well, but this is up to noise. So the question is, are these just...
Very little noise. Very little noise. Okay. This is strikingly close. Yeah, 3% noise. Okay, this is so this is an empirical finding. This is mathematically explainable. Yeah.
Did you come up with this open 9 versus?
No, I just made it up.
Yeah, but
there's a formula. in the model.
So that you see this empirically, you have to kind of combine the results from two runs of something like word to vec on one where you have the different ties and one where you have the
That's right.
different words. How do you compare them? Because I mean,
Every other word embedding is not changing. You're not changing. Yeah.
Okay.
You initialize everybody else with the same word embedding, and you just compute these words, the embedding for the new word. Yeah. Otherwise, because there's no up to rotation, so yeah, you would get junk. Yeah. Okay. So now this it turns out allows you to extract different meanings. Okay. So now we know that, or theory suggests and the experiment suggests that Tie1 and Tie2 must be in there, some of the meanings in linear superposition, which correspond to different representative discourses, okay, like clothing for one and drawn test matches for another or something. So it turns out you can do a linear algebraic procedure called sparse coding in dictionary learning, which again, I think the top audience must know very well. You find 2,000 discourses in this d-dimensional space, the 300-dimensional space. These are directions in space. 2,000, how do we come up with? It's empirically derived, okay? And the details are in the paper, such that every word vector is expressed as weighted sum of at most 5 of them. So this is assuming that we are only interested in resolving 5 meanings of the word, 5 major meanings. Sometimes words can have 10, 12 meanings. Okay, so this is just an approximation plus a noise vector. This is called sparse coding. And turns out this works very well. And that these 5 discourses that you find representing the tie correspond to the meaning. So let me just show you the examples. So these are some discourses that you find out of the 2,000 discourses. So here's a discourse: drowning, suicides, overdose, murder. These are ways in which people can die or be killed. Instagram, Twitter, Facebook, Tumblr, that's the social media discourse. So okay, what are these? So this is a direction in space, and these are the closest points, the closest words to that direction. Okay, so that's how I'm visualizing. It's a way of visualizing directions in space by the nearest word. This is social media. This is like horse racing. I didn't know many of these words myself. This is, it's actually a great learning thing. Like you look at these and see what are these words. Sometimes you really have to do a Google search to figure out. This is biology. This is like things you do, physical acts, classical music, conferences, meetings. So these are words, things, discourses that people talk about. 2,000 things that people. So they're kind of like fine-grained topics. Okay, so this I think connects back to something that people were asking earlier about what's the relationship to topics. So I think that's what's going on. And if you look at the 5 atoms that express tie, so this embedding for tie is expressed as a linear combination of at most 5 of these atoms, the 2,000 atoms plus noise. Okay, so that's sparse recovery. You can solve it. And here are the 5 atoms. So this one is a clothing discourse: trousers, blouse, waistcoat, etc. This is like tie as in like a game, season, teams winning. This is like a tied game, score line, goal less, equalizer, clinching, scoreless. This is tying cables, wires, etc. And this, I believe, is noise. Sometimes you do get junk, but some people also tell me tie is an important word in office. So who knows? Okay, so this is very typical. Okay, and we have quantitative experiments showing how this actually really does resolve meanings. Okay, I'm not saying this is the greatest and best way to resolve word meanings. Polysemy has many other techniques. But this does show you why word embeddings and how represent different meanings. Okay? Latest paper. Any questions, by the way?
Where's king and queen? Not in this.
Yeah,
Just out of
it is
curiosity.
2000. I don't remember.
But so how would that work with this? So the king and queen and man, woman?
So this is polysemy. So king, so let's see. So king may have, I don't know. King has multiple meanings. What are the multiple meanings? Yeah. Okay. So latest paper, sentence embeddings. Remember the example we started with, like the Pittsburgh and Carnegie and so on? Sentence embedding. So this builds on a paper also of Russ, weeding it out. Sentence embedding, which, oh no, sorry, this is not Russ, sorry. This is a paper from CTI, weeding it out, where the sentence embedding was average of the embeddings of its words. Okay, so that's a rough statement. This is actually a very gross simplification of what they did. But that already does surprisingly well. Okay, so you take all the words in the sentence and you take the average. This is a very crude description. So we wanted to come up with a sentence embedding, and I'll show you two applications that motivated us later. But first, let me give you the embedding. Okay, and so we try to come up with a sentence embedding, and it's not. I mean, it'll take longer to explain why we came up with this model. But what we realized is that the previous model is not quite correct, precisely because of somebody asked about frequent words. Those are the problem. Okay, the frequent words seem to occur just so there's a different process where like just popular words just happen to occur. So this model is now a mixture of two modes. So emission mode 1 is due to some kind of background probability. So every word has some background probability of W, and that is output in any discourse with some probability because of that, alpha times probability of W, and then beta times the old model. Okay, so you have a new model, and this is because you can see empirically that even if somebody's talking about the jungle, right, or hunting or something, you went on a hunting trip. In the evening, you brought out some cake and champagne, right? So cake appears in jungle, right? So words occur somewhat out of context a lot more than you imagine. Somehow that's what we discovered. So we came up with this. There was other theoretical reasons why this seemed correct. And the theoretical reason is the following, that this is a model where the max likelihood vector, a max likelihood estimate of the context C. So I'm giving you some sentence, so some context C, some discourse vector C, generated that sentence. So that max likelihood estimate is some kind of weighted sum of the vectors in it. Okay, beta sub W is some weighting depending on the probability, inversely proportional to the probability. So frequent words get weighted down. So this is our sentence embedding. Okay, this is our sentence embedding. You can compute these. You can find this parameter A, and then you can compute the weights beta W, and then you take this weighted sum of the vectors in the sentence. It's completely unsupervised. Okay, you just train on Wikipedia or something, get word vectors, word frequencies, and do it. And yet it beats RNNs and skip thoughts, etc. in some snapshots, as we'll see in a second. Any questions? So by the way, those of you who know about TF-IDF weightings, anybody, how many people know about it? Quite a few. So in information retrieval and NLP, people use TF-IDF weighting. This is very much reminiscent of that. Okay, and in general, it's a rule of thumb that in any NLP setting or information retrieval setting, you try TF-IDF weightings, term frequency, inverse document frequency. This is very much reminiscent of that. But in a word vector setting, it's not clear why TF-IDF should work, right? Here's a theoretical model that explains it. Okay, and turns out, oh yeah, I have that line. And turns out actually in the word-to-vec paper, the expression I gave you earlier is wrong. Okay, that's what everybody believes. The word-to-vec paper CBOW, the expression I gave, it's incorrect. Okay, that's what it's in the paper. That's what everybody thinks. But actually, the paper has some optimizations for the to make the whole calculation go faster, which involves sampling words. So everybody assumed that that was just for some efficiency purpose. But if you actually calculate the gradient that they are doing and the optimization they're doing this. And we present evidence in our paper that this is what's happening. Okay, and we learned this because I said, oh, now we have a better way of a better language model. Let's use word-to-vec and improve word-to-vec, and it didn't improve, and then we realized it's because they were already doing it. And you find that, I mean, the paper says it, but you have to really think hard to see why that's what they do. So here's some scores, so these are sentence similarity tasks, the textual similarity tasks, kind of like the opening slide, okay, the similarity of sentences. And these are R methods. These are all supervised or semi-supervised. Semi-supervised meaning that you train word vectors, and then you train the model by telling it these pairs of sentences, give the data set of similar and dissimilar sentences, and train it on that. That's semi-supervised, and supervised is even a little bit, I don't want to go into that. But anyway, so those models are not unsupervised. And our unsupervised model already beats most of them, except for this PP. And the semi-supervised version just is better for most tasks, except the last one. And then these are classification task. So you come up with a sentence embedding or paragraph embedding, and then you want to classify, sentiment analysis or whatever, entailment. So there are these prediction tasks, and then on there also, it does pretty well. Okay, this is completely unsupervised. So you don't need neural nets per se, you just need word embeddings, and then you do this weighted combination. That's actually pretty damn good, sentence or paragraph. So that was one motivation. The other one was, actually there's another one which I won't talk about, but that's ongoing work. But anyway, this was another one. So I think this line of work started here, Tom Mitchell and some neuroscientists, 6-7 years ago, that you're trying to relate fMRI readings of the brain to semantics in some way. Okay, so I won't describe the original Mitchell paper, which is very inspiring, but I'll tell you the experimental setup here, which is that, so fMRI is, remember, for those of you who don't know, is readings of blood flow. So you put a subject, completely conscious, awake, inside the scanner, and it's measuring blood flow at something like 50,000 points in the brain. Okay, so if you were to think of it in computer science terms, like you're trying to figure out how a processor works by measuring energy consumption at 50,000 points. That's basically what it's measuring. And so that you measure it, so you get this high-dimensional reading, and those are voxels. And so in this case, they were watching Sherlock Holmes. And the paper of Mitchell and then much other work says that you want to see how these fMRI readings correspond to the stimulus being presented. And the stimulus in this case is movies. What's a representation of a movie? I don't know. Probably Russ is much better at computing those. But even if you have a representation of a movie, it's not clear if the stimulus is sort of responding to what you're reading here is low-level things like loud noises or loud explosions or something, right? So is it responding, is the signal that you're capturing responding to semantics or to like low-level details about the scene or about the sound? So that was the question. So in order to focus on semantics, the movie scenes were annotated by people. Okay, so for every 5 seconds you have like a couple of sentences saying Sherlock and John are talking about the murder in an old room with Mrs. Hudson. Okay, something like that. So that's now the representation of the semantics of the scene. Okay, couple of lines every 5 seconds. Okay, and the human can only sit in the machine for like 10 minutes or 20 minutes, something like that. So you don't have a lot of data, and so it's a very low data setting. And now you're trying to correlate these fMRI signals to the semantics. Okay, correlate meaning, we'll see in the next slide. Okay, but it's clear, right? Some kind of like predict that from this or this from that. Questions? That's a rough setup. Okay. This being CMU, I think many people here have seen maybe something like this. Yeah. All right. So. Okay, so by the way, actually one important detail here which I don't mention is that actually you make 16 subjects sit in do the same experiment, and you actually combine the fMRI readings from the 16 subjects. That's actually a technique that was developed at Princeton by some other faculty. So so this is just a quick slide. There are these different regions of brain, and using our sentence. So you're trying to correlate our sentence embeddings or paragraph embeddings to the fMRI signal. You get some reasonably good. So this is like classification. So you are given. I think this is opposite because classification. Yeah, I think I got these. I this from the paper. And so classification is where you are given, let's say, an fMRI reading and the true annotation and a random annotation from some other point in time, and you have to say which one is the true one. So there you get accuracies roughly as high as 90% or 80% from the right region of the brain. And this actually my neuroscience colleague, Ken Norman, who's a co-author, was very happy with, because this is the area that the other studies had shown keeps track of narration in the story, like the thread, narrative thread, and this actually does have the highest correlation. So that was actually, they were very happy with this. And this is text to fMRI. Okay, so I think I'm out of time. Conclusions. So it's possible to do theory that addresses or explains behavior of seemingly intractable models, intractable in the sense of computational complexity, okay, and T-Hog and so on. for semantic coding, such as RNNs and RBMs. The empirical results are good. So for instance, our sentence embedding is the best purely unsupervised embedding we know of, and it even beats many supervised techniques. And it's completely transparent, fits to all intuitions like TF idea, which otherwise seem mysterious, but completely transparent from our theory or the analogy solving, etc. And, so this is, the fMRI thing, which is unpublished, appearing in the NIPS workshop, being sent to a journal. And so mostly for my theory friends, I think that it's great to embrace this new age of algorithms, which is being driven by experimental discoveries. There's amazing discoveries out there, and to try to do theory about it is really fun and thank you.
Any questions?
Yeah.
So for this sentence embedding, right?
Yeah.
You basically ignore the order.
Yeah. Does well. I agree. That's clearly not the right thing, right? Of course, word order matters, right? Man ate dog versus dog ate man. So what that says is that these tasks are designed to be very simple, so that it works. Clearly, the right answer is that you should look at word order and do everything that you guys did, but somehow the tasks are not capturing all those nuances, or maybe your models are too difficult to train and the simple model does better. One of the two. Yeah.
So because of this phenomenon with the analogy where you have some relationship, do you think what's been said for the
Stickiness, yes. I agree, that is probably true. And so there's two different things, right? So in the entire corpus, maybe that effect averages out. It's still the right way so that our model fits reasonably well. Okay? But when you actually try to use that model to infer what's going on in this place, absolutely, I think the wall is very sticky. And so, that's some other ongoing work which I'm not talking about. Yeah, that's not even written up and fully done. Yeah.
So my original question on, whether a given word appears twice, because I understand later on you said that you need a model for which frequent words appear more than once. That somehow that you generate those by some other means, or?
Oh, that was this model, right? So this one, right? This one. The frequent words actually will have some higher probability due to that term.
Okay. So what happens if you just have them appear multiple times on the sphere, on the embedding?
Oh, no, that's something else. Yeah, no.
That wouldn't be right.
That wouldn't be right, yeah. There's actually, yes. I mean, there's various cognitive science experiments which connect in a very nice way. I've talked to these people with this view of the semantic space as a sphere, and that there are these vectors, which actually are probably also, vectors also dynamic, right? As you grow up, your notion of a word changes, and so this is probably all fluid in the human mind, right? This space, the semantic space. So there's some nice connections to known facts and so on, which I didn't talk about.
So then there's two processes, one generating infrequent words and another generating frequent words?
They're both going on. It's just that that contribution for infrequent words might be smaller. Yeah.
Did you cite a linear language?
Sorry? Yeah. I mean, okay, so, oh, you mean the sentence embedding? Yeah, most of the sets probably, yeah. But word embeddings do work for other languages, that's wrong. Any question?
What's the version of embedding?
Yeah.
So this is trying to make the average talk and get a sentence. So it sort of begs the question of, well, there's sentences, but then there's paragraphs, there's books.
Yeah.
At what point does it not work?
Right. So that's what our ongoing work is trying. Yeah. So what I'm saying is that if you actually look at a piece of text and try to understand what's going on, our random walk model is probably not doing that. So it's doing some average sense, and so that takes a more nuanced view, which I can talk about offline.
Thanks again.